Assalamualaikum and hi, my name is FIRDAYS bin AWANGKU HARISYAM. I'm from group 9 and the title of our final project is hydrogen production via electrolysis. So here is our team member: Darren, DANE, JEFFRY, MUHAMAD, ALIF, HAIKAL bin PIEE, PROTASIUS, JAYVIER, MUKIAU, and myself. So moving on to the first chapter of our project. So starting from the research background, hydrogen is the most abundant element in the universe, and its role in energy transfer has become crucial as we shift towards renewable energy systems. One of the standout features of hydrogen is its clean burning nature, where the only byproduct is water. This positions hydrogen as a promising alternative to fossil fuels, particularly in sectors that are challenging to decarbonize, such as heavy industry, transportation, power generation, and a lot more. Numerous studies highlight that hydrogen plays a vital role in the global mission to achieve net zero emissions and tackle climate change. One effective way to produce hydrogen is through water electrolysis. This process involves splitting water molecules into hydrogen and oxygen using electrical energy. When this electricity comes from renewable sources like solar or wind, we refer to it as green hydrogen. This method is especially appealing because it can generate hydrogen without emitting greenhouse gases. It also provided the electricity used is sourced sustainably. A key player in the system is electrolyte, which facilitates ion movement across electrodes and significantly impacts the efficiency, cost, and scalability of hydrogen production. In hydrogen production system, different types of electrolytes are used, each with its own advantages and challenges. For example, the first one is alkaline electrolytes, commonly potassium hydroxide or sodium hydroxide. These are favored for their high ionic conductivity and low cost. While they are suitable for large-scale applications, they do face issues like material corrosion and lower energy densities. The next one is proton exchange membranes. These solid polymer electrolytes allow for compact and efficient design that integrate well with renewable energy sources. However, their high cost and shorter lifespan hinder broader adoption. So the potential solutions are innovative concepts like anion exchange membranes and hybrid organic-inorganic electrolytes are under investigation for their potential to deliver high performance while being less harmful to the environment. Improving efficiency and reducing costs in hydrogen production remains crucial for its widespread acceptance, even as electrolysis technology continues to advance rapidly. Moving on to the next subtopic, 1.2, the problem statement. So the hydrogen production through electrolysis is a promising avenue for achieving a sustainable energy future, but it does come with its challenges. One major issue is selecting the right electrolyte, as each type has its own advantages and disadvantages. Alkaline solutions like potassium hydroxide are commonly used in industrial applications due to their high ionic conductivity and low cost. However, their corrosive nature necessitates more frequent maintenance of the system. Seawater presents an abundant and accessible resource for large-scale hydrogen generation, particularly in coastal regions. Nevertheless, it requires desalination or chemical treatment to prevent corrosion and inefficiencies caused by impurities. On the other hand, mineral drinking water, which is relatively pure, serves as a middle ground option, but may not be economically viable for large-scale applications. Despite three options, there is still a lack of systematic comparisons regarding the effectiveness and functionality of these electrolytes under consistent experimental conditions. This gap is further complicated by the need to explore how different electrolytes interact with renewable powered electrolysis system. Given the variation in their operational parameters and energy inputs, identifying the most suitable electrolyte for hydrogen production, considering efficiency, cost, environmental impact, and long-term usability is crucial. To address this knowledge gap, our study aimed to evaluate the effectiveness of seawater, alkaline water, and mineral drinking water as electrolytes. And we will conduct systematic experiments to identify an efficient and practical electrolyte for sustainable hydrogen production. The insights gained from this research will be vital for optimizing electrolysis systems and promoting the broader adoption of hydrogen technology worldwide. The next subtopic is 1.3, the research objectives. So the primary objectives of this research paper is to identify the most suitable and environmentally friendly electrolyte for hydrogen production via electrolysis. To achieve this goal, the study will focus on three specific objectives, which is the first one is evaluation of electrolytes. The first objective is to systematically study and test seawater, alkaline water, and mineral drinking water as potential electrolytes. By measuring key parameters such as hydrogen yield, energy efficiency, and system stability under controlled experimental conditions, we will gather comparative data to assess the practical applicability of each electrolyte. This includes examining factors like ionic conductivity, reaction kinetics, and their compatibility with standard electrolysis systems. The second objective is environmental and economic impact assessment. The second objective is to analyze the environmental and economic implications of using these electrolytes. For instance, while seawater is plentiful, its pretreatment requirements could lead to increased cost and energy consumption. Alkaline water is effective but may pose challenges related to waste management and system corrosion. Additionally, the scalability of using mineral drinking water for industrial applications will also be evaluated. And the last objective is practical recommendations. The research aims to provide actionable recommendations for selecting the most relevant electrolyte based on specific application needs. By integrating experimental findings with theoretical insights, the study will contribute to designing cost-effective and sustainable electrolysis system. Though through these objectives, this research seeks to fill existing knowledge gaps and enhance our understanding of how different electrolytes can optimize hydrogen production in a sustainable manner. Moving on to the next subtopic, 1.4, the research scope. The scope of this study focuses on evaluating 3 different types of electrolytes, which is seawater, alkaline water, and mineral drinking water. Our aim is to assess their effectiveness under standardized conditions for hydrogen production using renewable powered electrolysis system. As for seawater is an abundant resource, particularly advantageous in coastal regions. However, its direct applications as an electrolysis solvent present challenges due to impurities that can lead to electrode corrosion and reduce system efficiency. To address this, our research will incorporate pre-treated seawater to mitigate these issues while examining its performance in hydrogen production. The next one is alkaline water. It is typically created using potassium hydroxide or similar solutions. It is known for its high ionic conductivity and reliable performance in industrial settings. This study will explore its efficiency and advancement and cost effectiveness while also considering the challenges related to electrode corrosion and waste management associated with its use. And last one is mineral drinking water, which has a composition that falls between seawater and alkaline water, offers the potential for low maintenance operation. This makes it appealing for small to medium scale applications. However, the research will also investigate the scalability and cost effectiveness of utilizing mineral drinking water in larger systems. To ensure consistency in our findings, we will establish a standardized experimental setup that minimizes variability in data collection. All 3 electrolytes will be evaluated based on key metrics such as energy efficiency, hydrogen yield, and system stability, allowing for a comprehensive comparison of their performance. Through this research, we aim to provide valuable insights into the most effective electrolytes for sustainable hydrogen production and contribute to the advancement of electrolysis technology. Coming on to the last subtopic of chapter 1, research significance. The significance of this research lies in its potential to greatly influence the sustainable energy landscape by advancing the production of green hydrogen. By identifying the most effective and feasible electrolyte, this study could significantly reduce the operational costs associated with electrolysis system. This is particularly crucial as the hydrogen economy expands, with various sector and government increasingly seeking to transition to more sustainable energy sources. So, moreover, the findings from this research may inform the design and development of next generation electrolyzers, enabling the structures to be tailored for optimal compatibility with specific electrolytes. If seawater emerged as a viable option, it could facilitate hydrogen production in areas with limited clean water resources, allowing these regions to invest in renewable energy solutions. Additionally, a clear understanding of the strengths and limitation of alkaline and mineral water electrolytes could enhance their targeted applications in both industrial and decentralized settings. On a broader scale, the result of this study align with global initiatives aimed at achieving climate goals such as the Paris Agreement and the United Nations Sustainable Development Goals (SDG). Specifically, it supports SDG 7 and SDG 13 by making green hydrogen more accessible and economically viable. Furthermore, this research addresses the growing demand for water-sensitive and renewable energy technologies, especially in regions facing water scarcity. In summary, this research not only contributes to the advancement of hydrogen production technologies but also plays a vital role in supporting global sustainability efforts and fostering a cleaner energy future.
Hello, my name is PROTASIUS JAYVIER MUKIAU, matrix number BK221100118, and I will be presenting Chapter 2 Literature Review and all of its content. Now for the theoretical background of the project. Electrolysis is the production of hydrogen gas through the process of decomposing water into hydrogen and oxygen using the application of electrical energy. Its performance is dependent on factors such as the type of electrolytes, electrolyte materials, and operating conditions. The battery electrolyte is responsible for the movement of charged ions from one electrode to another, a necessary process to maintain the electrochemical reactions. Now for the different types of electrolysis. For alkaline electrolysis, potassium hydroxide or sodium hydroxide solutions are typically used due to their characteristics of high ionic conductivity and low cost, ideal for industrial scale applications. For seawater electrolysis, direct use of seawater poses challenges due to its impurities with chloride ions, which can corrode the electrodes and lead to low efficiency. Seawater usually needs desalination or pre-treatment to be suitable for electrolysis. On the other hand, PEM system, which utilize solid polymer membranes, provide higher energy efficiency and compactness, but these membranes lack seawater compatibility. Another possible alternative, because of mineral water's higher purity and lower ion content, it has a potential for small-scale application, yet its effectiveness and economic feasibility for hydrogen production on an industrial scale have been less explored. Now for the factors that affect the performance of the electrolytes. Number one, ionic conductivity. Higher ionic conductivity minimize energy loss, leading to a improved efficiency of the system. Number two, electrode compatibility. Certain electrolytes are corrosive to electron, which require more durable materials to be used. Three, environmental impact. Byproducts and resource consumption are different depending on the type of electrolytes. Now I'll be presenting previous studies. Now for these previous studies, they were mainly focusing on testing three types of electrolytes, namely seawater, alkaline, and mineral water. These previous studies will assess their efficacy under standardized hydrogen production conditions by means of renewable powered electrolyte system. For alkaline electrolytes, especially potassium hydroxide and sodium hydroxide, have been investigated more extensively owing to their higher ionic conductivity and low cost. These electrolytes are commonly used in industrial scale electrolyte setting, with literatures noting their reliability and performance under standard condition. However, the researcher also listed challenges like electrode corrosion, material degradation, and the environment impacting the reliability. Although alkaline electrolysis is a well-established technology, in order to improve its sustainability, considerable improvements in waste management are needed. Now for seawater, it's a more innovative electrolyte, has garnered attention because of its abundance and potential for large-scale hydrogen production, particularly in coastal areas. However, its application in electrolysis is limited due to impurities such as chloride ions, which can cause electrode degradation and consequently lower the operation efficiency of the system. Pre-treatment or desalination frequently needs to be applied, increasing both the costs and energy demands. Studies have highlighted the generation of chlorine gas in the process of seawater electrolysis, a harmful byproduct, needs to have careful handling to avoid damages to equipments and to improve the purity of the end product. Nevertheless, seawater represents a great potential even in regions with limited freshwater sources, should affordable pretreatment technology be developed. Now lastly, mineral drinking water, because of its higher purity rate, has been considered for hydrogen generation as an electrolyte. Its low level of impurities make it less corrosive, requiring less maintenance and increasing the service life of electrodes. Nonetheless, the few studies that exist for its applications are mostly addressing small-scale setups. The application of portable water remains prohibitive on an industrial scale due to both cost and availability, making it an attractive, effective, but potentially complex candidate for specialized application requiring minimum operational complexity. Now I will be presenting a comparative insight, and I will be comparing the three types of electrolytes of their pros and cons. Now, out of all of the chemical electrolytes, alkaline water is the most effective and common chemical for the purposes in the industry. Its excellent ionic conductivity leads to a lower losses during electrolysis, making it a great candidate for large-scale hydrogen production processes. However, alkaline solution can be corrosive and may require durable electrode materials and a more routine upkeep that would raise the operational cost and environmental concerns over potential waste disposal. In contrast to that, seawater provides a plentiful economical source, especially in drier areas. While promising efficiencies have been attained with pre-treated seawater, they are still inferior to those of alkaline solution. This can be due to the residual impurities in seawater and the high energetic cost of desalination. One drawback of seawater electrolysis is generating chlorine gas that needs to be controlled by more sophisticated system. Despite these challenges, seawater is an attractive solution for large-scale application in coastal area, assuming pre-treatment process can be optimized for cost and efficiency. Now, on a smaller scale, mineral drinking water is an option that is not thoroughly explored, but it is showing promising results in specific situations. Because of its high purity, it reduces the risk of electrode degradation and minimizes the detection maintenance, facilitating operation in regimens requiring simplicity and less servicing. However, its price and ethical concern of using drinking water for an industry restricts its appropriateness to wider usage. The environmental and economic costs of using drinking water, especially for large-scale operations, are overwhelmingly more significant than its advantages, making it more of a niche solution rather than a first choice. Now, for each of the selections in the electrolytes, they should depend on the particular operating and regional circumstances. While alkaline water remains the go-to for efficiency, seawater provides a sustainable benefit in under-resourced area, and mineral water is increasingly targeting for use cases where not contaminating products with chemical is the main concern. A more nuanced understanding is essential for pushing the development of hydrogen production technology appropriate for different needs. I will now be presenting the hypothesis. Now, for this study, we have found that in literature that we have come up with a hypothesis that pre-treated seawater, when desalinated, is able to achieve a reasonable efficiency comparable to traditional electrolytes like alkaline water. Now, if the hypothesis is proven true, this will provide a great positive impact, since seawater is an abundant and ideal for coastal region. It is also a great alternative for renewable energy integration. Now, the pre-treatment process is anticipated to greatly affect the seawater's electrolysis process. It is expected to improve the performance and lifetime of the system by removing impurities such as chloride ion that cause electrode corrosion and unwanted byproducts such as chlorine gas. The hypothesis indicates that optimization of the pre-treatment techniques can minimize the challenges, making the seawater electrolysis competitive in a large-scale production approach, especially in areas with rich renewable energy resources capable of powering electrolysis and desalination. The energy efficiency of seawater electrolysis can be greatly influenced by the pre-treatment process. It is expected that the removal of fractions containing impurities such as chloride ions that cause degradation to the electrode and unwanted byproduct such as gaseous chlorine will improve the efficiency and the durability of the system. The optimized pre-treatment methods are assumed to mitigate these challenges, and thus seawater electrolysis is a potential option for future large-scale hydrogen production, particularly in regions where abundant renewable energy is accessible to supply the electrolysis and desalination process. Moreover, pre-treated seawater is unlikely to gain an equal ionic conductivity to alkaline electrolysis, but is more sustainable and represent a better trade-off between efficiency and corrosion. Such a seawater-based system would be useful to rapidly build up our hydrogen economy using seawater and its high availability without using expensive freshwater resources. It continues by speculating that improvements in electrode materials such as coatings that resist corrosion would make seawater electrolysis much more feasible with greater endurance and efficiency. The seawater pre-treatment and energy required for electrolysis hopefully can be balanced by coupling with renewable power such as solar or wind, making the whole process even more sustainable, especially in coastal regions. Renewable energy can be harvested from onshore and offshore facilities, making seawater an ideal source of water to fuel the production of green hydrogen via electrolysis.
Hello everyone, let's proceed with the methodology of our group project. Our group project evaluates hydrogen production efficiency in electrolysis using various electrolytes through experimental and mathematical modeling. Through this experimental and mathematical modeling, we were able to analyze the impact of operating conditions, material properties, and environmental factors on performance of the electrolytes. Our experimental setup consists of, first is the electrolyte, and second is the electrodes, where two aluminum electrodes are used and connected to a DC power source, where 4 AA batteries, providing an average of 5.88 volt. And directions observed at the cathode is hydrogen gas is produced, while at the anode oxygen gas is produced. For the efficiency calculation, these are the related formulas from the previous studies that help us to determine the volume of the hydrogen gas produced for every electrolyte. Before we construct our experimental setups, several preparations are need to be done beforehand. That includes cutting aluminum sheets, drilling holes to attach the bolts and nuts, and then attaching the wires, and secure with soldering, and reinforce with magnetic tape. And we also test for continuity. Electrode preparation and materials are shown in the figures. We prepare 3 pairs of aluminum electrodes, as shown in figure 1, and then we make holes in for bolts and nuts. Then we measure the voltage source across the electrodes to ensure the validity of voltage supply from 4 AA batteries. And then for the electrode and source wiring, we use soldering connections and reinforce with the electrical tape. There are 3 electrolytes we have chosen. First is seawater from UMS Odek Beach that is rich in salinity and ionic content that can enhance conductivity. But challenges like chlorine evolution and electrode corrosion are potential drawbacks. And then the second electrolyte we have chosen is alkaline ionized alkaline mineral drinking water. So it is selected because due to its high pH and enhanced mineral content, which are expected to improve conductivity and reduce energy losses. And the third electrolyte we have chosen is Prism mineral drinking water that can provide a comparison point against untreated freshwater sources. For our experiment, the manipulating variable is the type of electrolyte used, and responding variable are hydrogen production rate and the overall system efficiency. Control parameters include temperature, catalyst type, voltage supply, and the electrodes material, which is aluminum. And we standardize a 5% concentration of sodium hydroxide to enhance the conductivity and stabilize the pH levels. And for electrode materials, aluminum electrodes were chosen for their affordability and suitability for hydrogen evolution reactions. Next, the parameters we monitored were cell voltage, electrode behavior and stability, electrolyte and electrode interactions, and hydrogen gas production rate. For data analysis procedures, we first calculate the hydrogen production rate, whereby the volume of hydrogen gas generated will be measured by the displacement of the electrolyte during experiment. Then we calculate the efficiency by comparing the theoretical hydrogen yield based on the FIRDAYS laws of electrolysis to the experimentally observed volume of hydrogen produced. Then we evaluate the energy efficiency, where we calculate the energy input using the formula E equal to V times I times T. And then we analyze the differences in energy efficiency across the electrolytes to assess how their composition and properties impact performance. And then for trend identification and visualization, we use graphical representation. For example, we plot the graph of volume of electrolyte displaced in milliliter against times in seconds to visualize hydrogen production.
Hello, this is the results section of our presentation. Shown in Table 4 is the tabulated results for our electrolysis experiment using the prototype electrolysis prototype that we have built using aluminum electrodes. Table 1 to Table 3 are measured and calculated results based on the tabulated results that we have obtained from our experiment. We tested 3 different electrolytes: seawater, alkaline water, and mineral drinking water, and our focus was to understand their hydrogen production efficiency, practical applicability, and also the challenges of electrolysis within these 3 electrolytes. So this chapter doesn't just provide the numbers, but it also interprets the significance in real-world context, and we'll also discuss how each electrolyte performs, the factors contributing to their efficiency, and the implications for sustainable hydrogen production. Shown in Figure 1, it shows the graph of electrolyte volume displaced against time. So for these 3 electrolytes, we can see that the behavior and the trend line for the behavior of electrolyte volume displaced against time, it is linearly increasing for all 3 electrolytes. However, what is different is that seawater is faster in displacing the electrolyte, whereas mineral drinking water takes time, so it is slightly slower, at a slower rate. Next, we move on to the Figure 2 and Figure 3. Let's start with Figure 2 first. So Figure 2 illustrates the hydrogen production over time with these 3 electrolytes. So seawater's production, we can see that it is linear, starting at 6 milliliters at 20 seconds and reaching up to 31 milliliters at 100 seconds. This is because of its high ionic content, particularly with the sodium and chloride ions present in seawater. It enhances the conductivity and also the efficiency of the electrolysis. However, the presence of chloride ions introduces challenges, which is such as chlorine gas formation at the anode. So it needs careful management. However, it does not affect the hydrogen amount that we have obtained in our experiment, because chlorine gas is collected at the anode with the oxygen gas, whereas hydrogen gas is collected at the cathode. Moving on, alkaline water demonstrates steady production but at a slower rate, reaching up to 20 milliliters at 100 seconds. This is because hydroxide ions supports a controlled and is supported with a controlled and stable electrolysis process. This stability makes alkaline water a safer option, particularly in environments where consistency and minimal side reactions are critical. Hydroxide ions also increases the conductivity of the electrolyte, so this also supports why alkaline water is faster than mineral drinking water. Mineral drinking water, this electrolyte, has struggled due to its low ionic conductivity. It starts at 1 milliliters and reaching only 7 milliliters at 100 seconds. Even with the sodium hydroxide catalyst added with 3 of these electrolytes, its performance for the mineral drinking water is still limited. Continuing with Figure 3, the graph of hydrogen production rate against time. The production rates for the electrolysis for seawater. The seawater maintained at the highest and most stable production rate of 0.204 milliliters per second. We can see that the behavior of the trend line is straight and constant throughout the graph. This stability is a key factor for its potential in large-scale hydrogen production, but mitigating chlorine gas remains a hurdle because it requires more pre-treatment per se. Alkaline water has a consistent rate of 0.135 milliliters per second was observed, making it suitable for controlled environments. While its rate is lower than seawater, the lack of significant byproducts makes it a dependable choice for industrial setups. Mineral drinking water, however, with a rate of just 0.048 milliliters per second, it has the slowest rate of all the 3 electrolytes. It was inefficient and also energy intensive. The high energy demands reflects the inability to compete with the other 2 electrolytes in terms of scalability and cost effectiveness. However, the hydrogen production rate actually changes over a longer period of time. Because our experiment is only held for around 20 to 100 seconds, our results for the hydrogen production rate is almost constant, and there are almost minimal to no changes in hydrogen production rate. Moving on, we see in Figure 4, it shows the cumulative hydrogen production. This graph shows the cumulative hydrogen production over time. Starting with seawater, it leads the way with 61.3 milliliters at 100 seconds. And we can see that seawater demonstrates the most superior performance due to its natural ionic composition. The rapid buildup of hydrogen production highlights the seawater's potential for meeting industrial demands, particularly in coastal regions. Moving on is alkaline water. It has a cumulative output of 40.7 milliliters. It is a viable option for stable and safe hydrogen production, although it is slower than seawater. This makes it a practical choice for smaller scale or controlled applications where stability outweighs maximum efficiency. The last one is mineral drinking water. It produces only 14.8 milliliters. It is unsuitable for practical applications without significant modifications, which is one of the modifications include a higher voltage source, which is a higher current to the electrolysis setup. This result reinforces the need to focus on electrolytes with higher inherent conductivity for industrial scale hydrogen generation. So the expected outcome of our results almost supports our hypothesis. The expected outcome of this study was to identify the most efficient and sustainable electrolyte for hydrogen production. Seawater emerged as the most suitable candidate due to its abundance and natural ionic composition, which aligns with our hypothesis. Challenges like chlorine gas formation, however, must be addressed to optimize this application. Seawater's abundance and efficiency makes it a promising source for large-scale hydrogen production, especially in coastal areas. However, the environmental and operational challenges emphasize the need for further innovation in pretreatment and system design. So it requires more research in how the design of the pretreatment for seawater before it undergoes electrolysis for hydrogen production. Now let's compare seawater with alkaline water. So the performance between these two electrolytes. Seawater has yielded a higher hydrogen volume with up to 61.3 milliliters and a production rate of 0.204 milliliters per second. However, challenges include the chlorine gas formation at the anode and also electrode corrosion, which is one of the factors that influences the environment. Alkaline water has a moderate yield with up to 40.66 milliliters or 40.7 milliliters and a production rate of 0.135 milliliters per second. It provides a more stable and controlled environment with minimal side reactions. While seawater offers high efficiency, alkaline water predictability and safety makes it a more reliable choice for applications where stability is paramount. However, with maximum efficiency of hydrogen production, seawater is considered. What if seawater is considered as one of the large-scale hydrogen production electrolyte? So scaling up seawater electrolysis for hydrogen production involves overcoming several challenges. One of the key methods includes implementing advanced pre-treatment processes to remove impurities like chloride ions and other minerals. Also, one of the key methods we can do is develop corrosion-resistant electrodes, such as using titanium or nickel-coated materials or stainless steel is also viable. Also, we can also integrate renewable energy sources to reduce operational costs and environmental impact, as it also requires high energy source, but not as high as mineral drinking water. Addressing these challenges requires a multifaceted approach combining material innovation, system design, and sustainable energy integration to ensure seawater's viability to industrial scale. The role of oxygen in electrolysis. Did we address it? Hydrogen is the primary focus in our study, and oxygen plays a critical role still in electrolysis process. Oxygen is generated as a byproduct at the anode by the oxygen evolution reaction OER. It stabilizes the electrochemical system and ensures reaction efficiency. Potential industrial uses for oxygen could enhance the economic feasibility of the process because in electrolysis, in our study, only hydrogen is considered as an application for electric vehicles in the future or for future use in industrial applications. So in this study, the industrial use of oxygen is still not researched or elaborated. Although oxygen output was not primary focus in this study, its role in maintaining system stability and its potential as an industrial byproduct cannot be overlooked. The ways we can enhance hydrogen production with seawater electrolysis is by enhancing. It requires strategic improvements. So one of the strategies includes adopting advanced electrode materials for better corrosion resistance and efficiency, and also utilize nanotechnology to improve reaction kinetics and also reduce energy losses. Other than that, we can also implement intelligent monitoring systems for real-time optimization of operating conditions. These enhancements aim to maximize hydrogen output while minimizing environmental and operational drawbacks, paving the way for sustainable energy solutions. We can also use renewable energy integration like wind or solar. On electrolysis limitations with seawater. So although seawater is the potential of seawater as a large-scale hydrogen production electrolyte is good due to its high yield of hydrogen gas, the challenges are a lot still. This includes chloride ions. This is a side reaction, and chlorine gas is produced as a byproduct of this electrolysis of seawater as electrolyte. This is harmful to the environment, also harmful to humans. Other than that, high salinity accelerates electrode corrosion and reduces system lifespan. The high salinity of the seawater causes this corrosion and reduces the electrolysis system lifespan. Other than that, mitigation requires advanced materials and higher capital investment due to the higher quality of products such as aluminium, let's say nickel electrodes, or titanium or stainless steel electrodes. These are costly, and also the pre-treatment facilities that are involved in this pre-treatment to pre-treat this seawater electrolyte before electrolysis is also expensive, is very costly. So addressing these limitations is critical to unlocking seawater's full potential as an electrolyte, necessitating ongoing research and development. The pre-treatment of seawater is mentioned repeatedly. So it is essential but energy intensive. The process like desalination, ion exchange, and selective removal methods increases the operational cost of this electrolysis using seawater. Heat management is also crucial to prevent efficiency losses during large-scale operations. Variability in seawater composition adds complexity to the standardization. This is because different seawater at different regions are different in mineral composition. So finding the energy efficient and cost-effective pre-treatment solution is key to making seawater electrolysis viable for industrial applications. Lastly, the environmental compliance regulations and challenges. Large-scale hydrogen production using seawater addresses environmental and regulatory concerns. The key challenges include byproducts like chlorine gas and brine can harm ecosystems if not properly managed during the pre-treatment of seawater. Infrastructure and logistical requirements for inland hydrogen distribution adds complexity, like how would they distribute hydrogen gas across. And lower energy efficiency seawater has a lower energy efficiency compared to alkaline electrolytes, raises the operational costs. So meeting environmental standards while maintaining economic viability requires innovation in mitigation technologies and robust supply chain development.
So last but not least, for the last chapter, the conclusion. So in conclusion, our research highlights the remarkable potential of seawater as a resource for hydrogen production, especially as we strive towards a sustainable energy future. Throughout our study, we discovered that seawater emerged as the most effective electrolyte, generating the highest yields of hydrogen. This success can be attributed to its high ionic concentration, particularly the presence of sodium Na+ and chloride Cl- ions, which significantly enhance conductivity during the electrolysis process. However, while the results are promising, we also encountered several challenges that must be addressed. Notably, we observe issues such as electrode corrosion and the production of chlorine gas during electrolysis. These factors not only reduce the overall efficiency of the process but also raise important concerns regarding the environmental impact and long-term viability of using seawater in industrial applications. Despite these challenges, the advantages of utilizing seawater are compelling. Its abundant availability, particularly in coastal regions, makes it a sustainable and cost-effective option for large-scale hydrogen production. And unlike traditional alkaline water, which is limited in supply and requires extensive processing, seawater offers a more accessible alternative. And our findings further confirm that mineral drinking water was the least efficient option for hydrogen generation, reinforcing the idea that seawater is a more suitable candidate for this purpose. Looking ahead, it is essential to focus on optimizing pre-treatment processes to effectively desalinate seawater. This includes developing precise methods to remove chloride ions and minimize undesirable byproducts like chlorine gas. Implementing corrosion-resistant coatings on electrodes and exploring alternative material such as titanium or nickel alloy can significantly enhance both the durability and efficiency of electrolysis systems. Furthermore, we should consider integrating renewable energy sources such as solar or wind power with seawater electrolysis systems. This integration could not only improve the environmental sustainability of the process but also reduce operational costs, making it a more attractive option for large-scale implementation. In addition to these strategies, ongoing research into next-generation electrolyzer designs and intelligent monitoring system will be crucial. By maximizing operating parameters in real time, we can improve efficiency and scalability, ultimately paving the way for more effective hydrogen production. And in summary, while there are still challenges to overcome in utilizing seawater for hydrogen production, the insights gained from this project provide a solid foundation for future research. We can for future research and development in this area. By addressing these limitations and leveraging our findings, we can harness the potential of seawater electrolysis to contribute meaningfully to a low carbon economy and an energy resilient future. So that's all from us. Thank you.